So we have sound today. Can everybody confirm? You guys can hear and I can hear. Booyah! We are going to start by working homework problems. My first request is on ArcLink. Problem number 5 from WebWork. So I got to look up problem number 5 from WebWork. Firstly, we have 2 ArcLink formulas. Quiz yourself. In rectangular coordinates, ArcLink looks like what? Okay, but in polar coordinates, it's slightly different. We have the r squared here, and then the r prime squared here. Pay attention to which one you got. Both of them have a plus sign because it comes from the Pythagorean theorem. So that's one place where students typically make a mistake and put a minus in there. But then the other one is to forget the r squared in the polar version of this. And so, let's look at WebWork. Or does somebody have it open for me already? You got it? All right, what's my function look like?
Function is y equals x to the 2/3 power. From x equals 1 to x equals
27. All right. I'm going to find the length of the arc from x is 1 to x is 27. So y prime is 2/3 x to the negative 1/3. And when we put it into the rectangular coordinates version, the 1 and the 27 go here. And I got to take my y prime and square it. Just like that. When you square the y prime, don't forget to square that number in front. And then you square the x to a power by multiplying exponents. And so I'm going to get 1 plus 4/9 x to the negative 2/3. Raise a power to a power by multiplying exponents. So 2 times the negative 1/3 gives me the negative 2/3. In the next step, I'm going to write that x to the negative 2/3 with a positive power by putting it down there with a 9. So I've got 1 added to a fraction. We're going to get a common denominator and put our 2 terms together. So I'm going to think of that 1 out front as being 9x to the 2/3 divided by 9x to the 2/3. And now they have a common denominator. I'm going to write them as a single fraction. Okay, that's the common denominator step, putting them together as a single fraction. And if you have a fraction under a square root sign, you can take the square root of the top and the square root of the bottom. But I can't take the square root of the top term by term, so let's just leave that as 9x to the 2/3 plus 4, all under the square root sign. Then take the square root of the bottom and get 3x to the 1/3. Taking a square root is raising a power to a power. The power is a half. 2/3 times a half is 1/3. So I get 3x to the 1/3. I'm going to keep the 1 over x to the 1/3 inside. I'm going to bring the 1 over 3 out front. I'm going to write this as 9x to the 2/3 plus 4 all to the 1/2. Then I have the 1 over x to the 1/3 here and the dx there. It's that 1 over x to the 1/3 that's going to help me do this as a u du integral. Take u to be the stuff inside the parentheses. Then you'll notice that its derivative, let's see, 2 times 9 is 18. 18 divided by 3 is 6. 6x to the negative 1/3 dx. That's the x to the negative 1/3 dx. So I just have to divide through by the 6. And 1/6 du is my term that's in the last slot. Is that too fast? So we have 1/3 out front, u to the 1/2, and then this becomes 1/6 du. So I'm going to take the 1/6 from here, put it out with the 1/3, and get a 1/18. And now that's u to the 1/2 du. Integrate u to the 1/2 to get u to the 3/2 times 2/3. Two goes into 18 9 times. 9 times 3 is 27. And then u was 9x to the 2/3 plus 4. That'll all be to the 3/2 power. Then we evaluate that from 1 to 27. Let's go ahead and be finishers. One to any power is 1, so I'll go ahead and evaluate 1 to the 3/2. 27 to the 3/2 means the cube root of 27 squared. The cube root of 27 is 3. 3 squared gives me 9. So this number right here is 9. 9 times 9 is 81, plus 4 gives me 85. That's not a perfect square, so I'll just leave that as 85 to the 3/2. And 9 plus 4 is 13. That's also not a perfect square, so I'll just write that as 13 to the 3/2. So there's our arc length right there. You can put that into Webwork, and it'll like it. You ready to go back to 6-3 if you got another arc length?
No, I just have a question. So next week on the test, you want to show us proof just like
I suppose on the test you could probably stop here.
Sure.
Yeah. Right, we got an hour and 20 minutes. You got time to putz around a little bit. All right, next week is our test during our long hour or not? It is? Who's supposed to know, me or you? Whose job is it to know when the test is? Guess it's mine. Dang it. I'm gonna look right here, because I write things down sometimes. Let's see. Write things down this time. Here's I need to get that. I'll do that. Yeah, our test is on Monday, 1 week from today. So let's see how far we get today, and then I'll talk about what our test will be over. I'll put a review sheet of your test. Probably just chapter 6. We won't need the whole time. Here, flag me down so I can give you your papers back. Luke Blevins. Jay Hodge. Near side and far side field here. Make me dizzy. Lindsay Miller. Of course, it's all over there. Wait a minute, there's Jeremy. Matthew Cochran,
That was the one.
and Lucas Richmond. Right.
Then they get like the-
Oh, yeah. I didn't know.
We have to prove the, we have to prove.
All right, Paul, was it you that had the 6-3 problem?
Yes.
Yeah, like me.
And?
Like there's.
In area number 8, so the graphs for me, it was 1 plus cosine and then 2 cosine. And it was a graph outside of 2 cosine, but inside of 1 plus cosine.
Outside the circle, but inside the cardioid?
Yes.
Okay, so let's get a quick picture. Let's see, r is equal to 1 plus the cosine of theta. We can get a quick graph just by plotting the angles that correspond to the coordinate axes. If theta is equal to 0, cosine of 0 is 1, so r will give us 2. Cosine of pi halves is 0, so r would be 1 here. Same thing with 3 pi halves. And then the cosine of pi is -1, so that gives us 0 as the sum of 1 plus -1. And then the cardioid looks like this. That's the best cardioid I've drawn all day. The only cardioid, but it's still the best. R is equal to 2 cosine theta is a circle of diameter 2 on the x-axis. So I'm thinking it fits entirely inside, but I'm going to verify that it fits entirely inside by looking for points of intersection. If the circle butts out of here, then I'd find some points of intersection. So I'm going to do that first. I'm going to set these two equal to one another and solve for theta. I have 1 plus the cosine of theta is equal to 2 cosine of theta. Add the cosine or subtract cosine from both sides. And so cosine is 1 when theta is equal to 0 and 2 pi. So the only point of intersection is here and of course at the pole. I'll run through that. So that circle fits entirely inside. Oops, entirely inside, close enough. So my plan is just to take the circle out of the cardioid by finding the area of the cardioid. I can see what the area of the circle is, can you? What's the radius of that cosine circle? 1, so the area is pi times 1 squared. So the area of the circle So I'll just do that at the end. I'll take the pi away at the end. Let's just find the area of the cardioid. The cardioid took me an entire lap around the unit circle to graph, so I'm going to integrate from 0 to 2 pi of the 1 plus cosine theta. But I need to remind you of the area formula. It's 1/2 of f of theta squared d theta. So there's the 1/2, and then I got to square the 1 plus cosine theta. When you square 1 plus cosine theta, you get 3 terms. You get 1 plus 2 cosine theta plus the cosine squared of theta. And now we can integrate term by term. going 0 to 2 pi. You integrate the 1 and you get theta. Integrate cosine and you get sine. You get two terms when you integrate cosine squared. You get theta divided by 2. Cosine has a plus here. And then the sine of 2 theta divided by 4. The two sine terms in there don't give us a thing because the sine of 0, the sine of 2 pi, and the sine of 4 pi are all 0. So when I put these substitutions in here and here, I get a bunch of zeros. So I'm going to get 2 pi plus 2 pi over 2 times a half. So in the box here, I have 3 pi times a half gives me 3 pi over 2. So now the area that I seek out here is going to be cardioid minus circle. So the cardioid was 3 pi over 2. The circle was pi. 3 pi halves minus 2 pi halves gives me pi halves square units of area.
Did it the first time, this makes a lot more sense than doing it, but like all in the integral where it was outside squared minus inside squared.
The only problem is the circle's traced out on a different interval. We trace the circle out by going from 0 to pi done twice. If you go 0 to 2 pi, you're going to get too much area out of your circle.
Okay.
If you want, you can integrate the circle from negative pi halves to pi halves on the circle. But they had different limits of integration.
Okay.
That's the way I did it. I got a negative area at the end, so I just put it around. I got my answer. But the way it happens is like I only did it from 0 to pi, I multiplied by 2.
Right.
But I did outside minus inside. I did like the cardioid minus the circle. So I thought that'd be all right, but I still got like the negative value.
Let's see why that happens. Because on 0 to pi, you're getting the circle done twice. This whole circle is traced out already just once on 0 to pi. From 0 to pi over 2, we get the top half of the circle. From pi over 2 to pi, we get the bottom half of the circle. So you've actually gotten this done too many times when you integrated from 0 to pi and then doubled it.
Okay.
And because of the symmetry of the numbers, 3 pi over 2 minus pi and pi minus 3 pi over 2, you really got pi minus 3 pi over 2 and it was negative.
Yeah.
So it's not always going to be so easy as changing the minus sign.
Okay.
You have to kind of be aware of the sizes of these things and when they're traced out. Yes. Kinda. It worked because you had a cosine, right? It's not going to work if you have a sine because of the symmetry of the cosine. But if you're integrating 3 pi over 2 to pi over 2, you're actually getting this stuff out here. And when you're integrating out here, those values of r are plotting this circle back here. But they're only plotting this part of the cardioid here. So you got to be real careful. Yeah. Or write the circle separately if it doesn't share the bounds on the integral. Because if I said, find the area inside this circle, you would never set that up from 0 to 2 pi, right? If that was your singular problem, you would see that circle sitting over there, and you'd say, oh, I can integrate from minus pi over 2 to pi over 2. So that's the mistake in sharing the integral if they have different limits on the integral. So if it does help, do them separately. But sometimes, because our trig functions are so nice and symmetric, you can kind of finagle with the limits on integral and do the wrong thing and get the right answer. And so I'm not going to punish you for doing the wrong thing and getting the right answer because I know how right answers make you so happy. But if on the test I say, set this up, and you set it up incorrectly, then I'll bust you then. Right now, we're still all happy and good. But kind of pay attention. You got another one somewhere? Yes, sir.
It was number 6 on the web where it goes sine theta plus cos theta on 0 to pi.
You want to find the arc length? So we're going to use this arc length formula because we've got r's and thetas. So we need an r squared and an r prime squared. So let's go ahead and get r prime. So r prime looks like cosine of theta minus the sine of theta. Let's put them into our arc length formula here. You know what number this one is? That's section 6.4. So here's my formula. There's my r and my r prime. So my arc length will have the integral from 0 to pi. Sine theta plus the cosine of theta all squared. Plus, now my r prime is cosine theta minus sine of theta, all squared, under the square root sign, and integrate. There's the setup. Now comes the fun part. We're going to do all the squaring. When you square sine plus cosine, you're multiplying it with itself. So you're going to FOIL it out and get 3 terms. You'll get the first term squared. You're going to get 2 times the inner product. So you get 2 sine theta cosine theta, and it'll be plus. And then you'll get the last term squared. Now we're going to do it again. In here, you're going to get the first term squared. 2 times this product, so it's 2 times cosine times sine, but with a minus in front. And then you get plus the last term squared. And all of that is under one jumbo square root sign. In the integral, slap on a d theta. So there's a couple of things you can notice. One thing is 2 sine cosine minus 2 cosine sine, those are the same. So they add each other out. Then you look at what's left. I've got a sine squared plus a cosine squared. So I know that adds to 1. I've got a cosine squared to a sine squared, so that adds to 1. I just have 2 underneath the square root sign. So I'm integrating the square root of 2 d theta. That's a constant. The integral of the constant is the constant times theta. The pi in there and put a 0 in there, and you just get the square root of 2 times pi as my arc length unit. Find another one. All good. Good work going once. Going twice. All right, good work going. So now we're going back to section 6.5, and we're computing work integrals. The idea was that force varies in what we're doing. So we cut our integral up into little tiny pieces, and we multiply force times distance over the itty bitty teeny tiny pieces, and out comes an integral that looks like the force times the distance. We have to figure out what these are. With the spring problems, the force was given by Hooke's law. Did we do any pumping water problems yet? None of those, but we did 2 spring problems. Okay, so I had a handout with some problems written on it. I've got a handful of them left. If you didn't bring yours with you and we want a copy of the problems, anybody want a copy of the handout? I think I've got these all worked for you on Blackboard. So you can watch it and watch.
Did she do that?
Wow, so hard.
I think it's- Yeah. That's what I did. With mine, but I didn't know if that was good.
Any more fingers? Okay, did we work number 1 and number 2, and then your 2B I just wrote on the board and I put it on the handout where I worked the second version of the spring problem. We got to number 3, so we're going to do some work in pumping water. So if we're going to be pumping water from a container, then what we're going to do is we're going to set our container on a grid that helps us set up an integral. And so I'm pumping water to the top of the tank or above, so I'm going to do everything up the y-axis. The idea is it takes more work to move water from the bottom of the tank to the top than it does from a higher level to the top because it has less of a distance to go. Remember, work is the force times the distance. This liquid that's in the tank, whether it's water or any other liquid, has some sort of weight density. Well, if we're in our United States units, the weight density will be some sort of volume measurement per cubic pounds or something like that. So that will be a weight density. If we're doing problems in the metric system, then you're going to be given mass density. And you've got to include the gravitational constant as part of the mass density to make it into a weight density. So when we're in our English units, I think I've given it to you in the right ways. Anyway, we're going to take our liquid and we're going to look at a thin slice of it. And I'm going to slice it across the tank perpendicular to the y-axis. So that each slice of liquid has whatever shape the tank is generating and a thickness of a dy. I'm going to find the volume of that slice. That'll be in cubic units. Then the weight of that liquid is going to be in pounds per cubic units. So when I take the weight of the liquid times the volume of the slice, I'm going to get pounds. Pounds is our unit for force. Then we need to figure out the distance that one slice has to move to get it to where we say we're going to put it, either the top of the tank or above the top of the tank. In which case, that gives me the distance. So this time, distance is going to be a function of y. And the dy is going to come from the thickness of the slice. But it's still setting up force times distance. Now, can anybody repeat what I just said? Is that Charlie Brown's teacher? And why didn't I just do that? When I just stand up here and say, wah, 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 wah. My gosh, here's what I just said. Okay, so we've got, our goal is to find the work done pumping liquid out of a tank. So whatever the tank looks like, for now it's just gonna look like squiggly lines. We're gonna put it on the y-axis. Of course, it's got some sort of three-dimensional shape. It could be roundish, it could be a rectangular shape, but it has some sort of three-dimensional shape, but I put it as a 2D shape. Say it's got liquid, say the tank goes from the origin to some height h, and the liquid goes to some number, I don't know, b. We make a slice of the liquid. When you pull that slice out, it has some three-dimensional shape. I don't really know how to draw the three-dimensional shape unless I specify what the tank looks like. But the thickness of the liquid is going to give us our delta y. Our liquid has some sort of weight. Of some number of pounds per cubic feet. And if we take the weight density and we multiply it by the volume of the slice, so we'll have to figure out the shape of the slice. So it's going to be whatever the area of the face is. You have to pull it out and look at it. It might be a rectangular slab, it might be a circular slab, or some version of it. But then you get the volume of the slice, that's going to be in cubic feet. And so the product of those kind of units give us the force. And then we see how far we have to move that slice, and that depends on the problem. It will tell us, are we taking it to the top of the tank? Are we taking it over the top of the tank? But I've got it at some random y coordinate. And suppose I just want to take it to a height of h, then the distance that the slice moves is the total distance of h minus y. And then if I'm in English units, and I'm going to say that that's in feet. So I've got my force times my distance. So I've got pounds of force, feet of distance, and I sum them up over the depth of the water. And so the work is equal to the integral. The integral reflects the depth of the water, or whatever liquid we have in the tank. So in my picture, I've got it going from 0 to b. That could be whatever, again, that could change according to the problem. And then you've got your force, which is the density times the volume. It's the volume of the slice of liquid, not the volume of the tank. Those together give you the force. Then you've got your distance. And as part of the volume of your slice, you'll get your dy term. And so we'll integrate this up the y-axis. We try to place our tank on the coordinate system so that it makes figuring out the volume of the slice the easiest. So in our first example, problem number 3, we've got a cylindrical tank of diameter 4 feet and height of 6 feet that's half full of water weighing 62.4 pounds per cubic feet. So here's my tank of water. I think it's easy to put the coordinate system so that the origin is right here and the y-axis comes up through here. And I said the tank is a grand total of 6 feet high. So if this is the origin, then this corresponds to the ordered pair 0, 6. And then it says it's got a diameter of 4 feet. And so that means the radius is 2 feet. So if I come out over here in the XY plane, then that would be 2 feet away. So that's the ordered pair 2, 6. Then we're told that it's half full of water. So the liquid goes to a depth of 3 feet. And we are going to take that liquid and empty it over the top of the tank in the first part. We want to take the liquid from where it is to a height of 6 feet. In the second part, we want to pump it to a level 2 feet above the top of the tank. So in the second part of the problem, we're going to pump the liquid from where it is to a height of 8 feet. So we're going to pump to here second. Two separate problems, just with one subtle difference. Now the tank determines the shape of the slice. So I'm going to get out and I'm going to make a slice of liquid. I'm here at some y coordinate between 0 and 3. I'm going to run a slice through that liquid and it's going to take on the shape of a tank. Of thickness delta y. So a slice is a circular disc. Of thickness delta y. And so, according to my game plan, I'm going to take that weight density, which is given as 62.4 pounds per cubic feet. Take the pounds per cubic feet, multiply it by the number of cubic feet of volume of water in that one blue slice of water. The volume of a circular disc is the pi r squared times the thickness. At any stage of the slicing, the radius of the slice is going to be the same as the radius of the tank because the sides are straight up. So the volume of my slice of water is going to be pi times 2 squared, right? The radius is 2 times delta y. Now I'm going to take the slice from where it sits and in part A, take it to the top of the tank. So here's a height of 6, and I'm going down to a height of y. So how can I write the distance that that one slice travels? 6 minus y. I need to take it to 6 feet, and it's currently at y feet. Distance is in feet. So if I take volume, which is in cubic feet, multiply it by pounds per cubic feet. The cubic feet cancel, and I get pounds of force. Multiply that by feet, and I have pounds times feet, which is my work units. So the units themselves are telling me how to set up my integral. So work is the integral of force in pounds times distance in feet. So my force in pounds, I said, was the 62.4 pounds per cubic feet times the number of cubic feet, pi times 2 squared. And when I get to the integral, the delta y becomes the dy. So this now is cubic feet. And now the distance was 6 minus y feet. Cancels the way I want it to. Pounds times feet. The number on the integral sign represents where I'm doing the slicing, and that's through the depth of the liquid. So I'm only going to slice on my y-axis from y is 0 to y is 3. So I put 0 to 3 on the integral sign. Now everything in this integral is a constant, 4 pi 62.4. I can pull that out, and all we're integrating is 6 minus y. The integral of 6 minus y is 6y minus y squared over 2. From 0 to 3. So I'm going to have 18 minus 9 halves. But 18 minus 9 halves is I don't know, 36 minus 9 over 2. 27 halves. And that units would be foot pounds. To the top of the tank. That much work to get it to the top of the tank. Yes.
Could you explain why we use 3 as the limit again?
The slicing, we're moving the liquid. So I don't need to move anything that's air. I just make slices through the liquid.
Oh, okay.
And then we're told it's half full, so I can stop slicing it through. Now, when I pump it to the height 2 feet above the top of the tank, we're assuming that the shape of the slice doesn't change. It's going to stay its circular disc. So you got to suspend disbelief a bit. We've got our circular disc traveling up here magically, Harry Potter style. We're not going to put it through a separate shape of a pipe. So the only thing that's going to change, this disc keeps its same size. The only thing that's going to change is how far it travels. So to pump it to here, instead of to here, it'll travel a distance of 8 minus y. So in part B, when I pump it higher, the new distance is 8 minus y. So I get the same integral, we just make this an 8 minus y here to pump it 2 feet above the top of the tank. Okay? Now, in reality, we'd have to be told what kind of pipe it goes through to get it to the top, above the top of the tank, and then we'd have to change the shape of the slice, and that just adds all kinds of gunk to the problem. So we'll just assume it floats up there as a perfect circular disc. What if I had the same tank, half full of water, and I'm told I'm only gonna pump the top 1 foot of water out of the tank. I'm gonna leave 2 feet of water in there. I just wanna pump the 1 foot of water out of the tank. Then I make my slices from 2 to 3, right? The shape of the slice doesn't change, the distance doesn't change, and I'm just pumping the top part of the water out. I integrate from 2 to 3. Okay? So all of these problems are going to look like density times volume of the slice times distance. We already out of time for this beautiful classroom. Let's go down the hall. I thought, why are they leaving? Are they getting tired of me? Well, don't answer that. Just leave. All right, let's move on. All right, let's have this video and move to the next classroom. Right